Hello, welcome to Econometrics Melody. In this video, we will discuss on how to estimate the difference in means of two normal population when the population variance is unknown. And we know that the sample mean, it is distributed normally with mean mu and variance sigma squared divided by n. And in this case, we assume that the variance of the population is known. We can construct a z-score out of it as x bar minus mu divided by sigma divided by root n, and sigma divided by root n is the square root of the variance of the sample mean. And this z-score is normally distributed. It has a standard normal distribution with mean 0 and variance 1. In this case, we assume that we know the variance of the population. Similarly, when we don't know the variance of the population, we estimate it making use of sample variance, and we know that the sample variance n-1 s square divided by the population variance. This has a chi-square distribution with n-1 degrees of freedom. So when the population variance is unknown, the sample mean, it has a t-distribution with mean mu and variance s square divided by n. And it seems like we are simply substituting the population variance by the sample variance, but in fact the t-distribution, it is calculated making use of the ratio of standard normal distribution divided by the square root of the chi-square distribution divided by its degrees of freedom. And let us see the internal process of calculating t-distribution with reference to these two conditions stated above. This is equal to, so our z-score, it is equal to, and we further divide this by our chi-square distribution. So our chi-square distribution is n-1 s square divided by sigma square and its degrees of freedom. So let us write it as, and if we further divide it by its degrees of freedom, so this is further equal to, and if we further divide this by n-1, this is equivalent to multiplying it by, so n-1 it cancels out, so we are left with, as n-1 it cancels out, we are left with square root of s square by sigma square. So this is equal to s divided by sigma, which further is equal to, and as this sigma it cancels out, we are left with, so when the population variance is unknown and we estimate making use of our sample variance, so in that case, instead of a z-score, we get t-score. So the z-score, it turns into t-score with n-1 degrees of freedom. And in place of population variance, we estimate it making use of the sample variance in this relationship. Also, for two independent normal populations, the difference in their sample mean, it is normally distributed with mean µ1 minus µ2, and the variance is they are independent. Variance is equal to sum of their individual variance. And from this relationship, we can always construct their z-score. So the z-score, this is equal to x bar minus y bar minus difference in their population mean, and we divide it by the square root of their variance. This term is their variance, so square root of it. So this is equal to, so let us term this entire term in the denominator as a. Then we can construct their confidence interval. So the confidence interval of the difference in means of two independent normally distributed population. So this is equal to x bar minus y bar, and to this difference in their sample mean, first of all we subtract z alpha by 2 and we multiply by its root under variance. So this is equal to, we have assumed it to be a for the time being. This a is equal to square root of sigma 1 square divided by n plus sigma 2 square divided by n. This is our lower interval, and the upper interval is, so in this case we have assumed that the variance of the population, they are known. So we will now concentrate on estimating the confidence interval of the difference of the population mean when we don't know the variance of the population. First of all, let us see, when we know the variance of the population, then in that case we calculate the variance of the difference between the sample means of two independent population. This was equal to the sum of their individual variance. For the single sample, when we know the variance, we constructed the z-score as, and when we didn't know the variance for the single sample, we constructed the t-score as it had n-1 degrees of freedom. And we have already seen how did we calculate this t out of z-score, where t was equal to the standard normal distribution divided by the chi-square distribution divided by its degrees of freedom. Similarly, when we don't know the variance of the population in case of two samples or two populations, so we may want to write as es1 square divided by n plus es2 square divided by m. When the variance is unknown, we cannot write it in this way, because in this case we cannot calculate the distribution of it. So in that case, in order to be able to calculate the variance of the difference of the sample means of two different normal populations, we'll have to make an assumption that though their variances, we don't know about their variance, we can assume that their variance are equal. So let us calculate the z-score for this condition. We are calculating z-score assuming that we know the variance of the two normal populations, and that is equal to sigma square. So the z-score would be equal to, now in fact, as we don't know the variance but we are assuming them to be equal, so how do we estimate the population variance in that case? So in that case, we make use of the procedure to estimate the population variance when we don't know it. So in that case, it has a chi-square distribution with n-1 degrees of freedom. Similarly, m-1, so this one is for the first population, and for the second population it is equal to, and this has a chi-square distribution with m-1 degrees of freedom. So if they are independent chi-square, then the sum of the independent chi-square, so here plus this has also a chi-square distribution, and the degrees of freedom is equal to the sum of the individual degrees of freedom. So this is the independence version of the chi-square distribution. So the sum of the two independent chi-square distribution is also a chi-square distribution with the degrees of freedom equal to the sum of their individual degrees of freedom. Therefore, this has a chi-square distribution with n plus m-2 degrees of freedom. Now we know a chi-square distribution related with the variance of the two populations, first population and second population, and we know its degrees of freedom. So the degrees of freedom is n plus m-2, n plus m-2. Now we can construct the t-score for this. So the t-score, this is equal to standard normal distribution, that is the z-score, divided by root under chi-square divided by its degrees of freedom. Now let us calculate the t-score for this condition. Therefore, t is equal to its z-score, this z-score, divide it by square root of chi-square. So what is our chi-square? m-1 es square plus m-1 es square divided by sigma square. This is our chi-square, and we need to divide it by its degrees of freedom. So this is n plus m-1. And this t-score, it has n plus m-2 degrees of freedom. So this is for the equal to. So here sigma square is common, and if we take it out of the square root, so we are left with sigma root under whole divided by root under n-1 es square, es1 square they cancel out. And let us suppose that this term, this is equal to, so this will be equal to, and this is again equal to. In this case, we are assuming that we don't know the population variance of the two normal independent normally distributed population, but they are equal. So we can construct the confidence interval of the difference in means of two independent but normally distributed population. This is equal to, and we multiply by the square root of their sample variance, and that is equal to, so this is our lower limit interval, and our upper interval is, and the confidence level is 1 minus alpha. Now let us see if we have committed any kind of mistake. A random variable x, this represents n number of Bernoulli random variables. Then for large n, this is approximately normally distributed with mean np and variance np1 minus p. So its z-score is given by, so if we compare it with this, z is equal to Then x bar is the sample mean. So here this x is the sample mean. Let us substitute the sample mean n into the proportion of success minus np. This is population mu. We divide it by root under np1 minus p, and we can transform it as, and we divide it by n squared because we have taken n common from the numerator and we kept it to the denominator in this way, and this is further equal to, therefore z is equal, this is equivalent to sample proportion success minus p proportion of success for population divided by root under, and from this relationship the confidence interval for the population proportion of success or the probability of success, this is given by the upper interval, and the confidence level is 1 minus alpha. And if we compare it with the confidence interval of population mean. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.